Okay, welcome to lecture. We'll get started here in just a second, continuing on chapter 4 where we left off. Again, type here in the chat box for roll. Okay, so we were talking about geometry here, and we started talking about it last time. And remember that we look at geometry and we could kind of identify our geometry for our molecules based on the Lewis structure that we draw. And when we do geometry, there's really two types of geometries that we look at, or two types of sort of names, if you will, for geometries. One, again, is the electron pair geometry or electron pair arrangement, sometimes referred to. And again, that describes around the central atom how many total electron pairs there are. So it's basically the arrangement of just the electrons around the central atom. And then we also have the overall shape, or molecular geometry is sometimes referred to, and that's the overall shape of the molecule. So as those electrons sort of move around and sort of try to get themselves in the optimal position, if you will, for their particular arrangement, the overall shape of the molecule kind of moves around and changes a little bit. And when we do geometry, there's really a couple of things that we want to kind of make sure of. And the first one is when we do draw the Lewis structure and we do have a double bond or a triple bond, when we kind of go around and count around the central atom, the double bond or triple bond counts as only one electron pair and also one bond as well. So again, specifically for geometry, if you do have a double bond or a triple bond, just count it as one electron pair and one bond. The other thing is we also talked about is if you drew more than one sort of resonance structure, you can do obviously this geometry to either one of them. And in practical aspect, usually you should end up with the same geometry regardless of which resonance structure you should draw it for. But the main thing really when you're doing geometry is just that the double bonds, triple bonds count as only one effective bond and one basically electron pair. Now, they are sort of broken up into two different categories in terms of molecules or structures, and that's one where there are no lone pairs or non-bonding electrons on the central atom. So again, what that essentially means is when you draw the Lewis structure, you have no dots there on the central atom. And when you do have that situation, you pretty much have only bonding electrons involved. So you have bonding electrons, near bonding electrons. And as we talked about, that's sort of the, I would say best, I guess is maybe the wrong word there. That's sort of the okayish in terms of electrons being near each other. Remember, the whole idea of geometry is the idea that electrons are obviously negatively charged, which means when they do get near each other, they really don't want to be there. So they do want to kind of spread out as best as they can do. But they can't necessarily get completely away from each other because they're still obviously locked into a bond. So they do try to, again, get as far away as possible in those situations. So when we do draw a Lewis structure and there's no dots on the central atom, no non-bonding electrons or lone pairs, the electron pair geometry name and the molecular shape or geometry will be the same. So those names will be the same. It's only when we start getting into non-bonding electrons around the central atom that we do get some differences in terms of the names. And that's because at that point, once you introduce those non-bonding electrons, you're introducing several different types of interactions that are happening with electrons. You have, again, bonding electrons near bonding, which is okay. You then can get non-bonding electrons near bonding, so dots near lines in your structure. And you also could get sort of the worst situation when we talk about electrons being near each other, And that's when we get non-bonding electrons near non-bonding electrons. And those guys definitely want to kind of spread out as far as possible. So the one name that really doesn't change is the electron pair geometry. That name doesn't change. But the name that is affected is the molecular geometry, or the molecular shape does get affected by that non-bonding electron sort of spreading out. So when we do draw a Lewis structure and it has dots on the central atom, those two names will be different. So electron pair geometry name and the molecular shape will be different when you have those non-bonding electrons involved. And that's sort of where we left off here. We also started to see those exceptions to the octet rule. So especially those expanded octets where they could go greater than 8 around the central atom. Remember, on the periodic table, those are guys around sulfur, kind of to the left and right and down. Those are the ones that have the ability to do the expanded octet. Again, get 5 electron pairs around it, which would get you triangular bipyramidal, or up to 6 electron pairs, which would give you that octahedral geometry. Again, those expanded octets have a lot of geometries that are associated with it. Any questions on any of that stuff we talked about last time, I think? Okay, so I think this is where we left off. So again, just looking at this, remember that when you do geometry, it is really just the central atom that's the important one. So you always want to go to the central atom. In a lot of cases, you'll just have one central atom, but it is possible to have multiple central atoms. So it is possible to have more than one. So for example, here, if we looked at our central atom like I did there on top, kind of drew it out again, total electron pairs, doesn't matter if they are lines, doesn't matter if they're dots, so it doesn't matter if they're bonding electrons, non-bonding electrons. The total electron pairs, again, around that central atom in this example is 5. And again, something with 5 electron pairs is what's known as triangular bipyramidal. Again, that's the expanded octet that has obviously 10 electrons around it rather than 8. And when we look at this, though, it does only have 2 bonds. So the bonds to be in the lines. So something with 5 electron pairs and 2 bonds. In terms of the molecular geometry, it actually becomes linear. And that's because there's a lot of sort of freedom between everybody. There's only 2 bonds. So those bonding guys can basically separate as far apart as they can, which would give them kind of a 180-degree difference between them. But it allows these non-bonding electrons to also spread out almost in a triangle type arrangement here as to how they sort of spread out. And we get this geometry here, which is linear. So again, the electron pair geometry name is really based off of the number of electron pairs there are. It doesn't really change. So basically for us, that's basically you'll have 2 electron pairs, which is linear. You'll have 3 electron pairs, which is trigonal planar. You'll have 4 electron pairs, which is tetrahedral. You'll have 5 electron pairs like we see here, which is triangle bipyramidal. And you'll have 6 electron pairs, which is octahedral. So in terms of the electron pair geometry, it's pretty straightforward. You just count the number of electron pairs and pretty much match it up to the correct name there. Again, it's that molecular geometry name here when we get those non-bonding electrons that does have a tendency to change. All right, so let's take a look, I think, at the next one here. So the next one here, if we draw it, we have a central atom. And again, when we're doing this, we do want to look at our central atom right here. And if I draw it sort of just the central atom, it looks something like this. So again, if you just kind of super zoom in there on our central atom, we got 1, 2, 3, 4, 5 electron pairs. In this case, though, we have 1, 2, and 3 bonds. So again, here in terms of the electron pair geometry, which is based solely on the number of electron pairs, we're going to have 5, which again, as you can see, there is our triangular bipyramidal. But now we have 3 bonds here. And we have those non-bonding electrons. So again, those three bonds are going to try to get away as they can as far as possible, while these sort of non-bonding electrons sort of head out that way. Remember, as sort of one thing moves, since everything is bonded together, everybody else will sort of move appropriately with it. And we get this shape, as you can see, which is sometimes referred to as T shape, as you can see there. And that's because, again, if you look at it, it makes kind of like an upside down T, right? If you do it that way, sort of that T-shaped geometry. Again, here with the 5 electron pairs, another expanded octet geometry in terms of what you got going there. Obviously, you can see kind of a 90-degree sort of angle happening here. And these are sometimes what are referred to in terms of their position, axial, sort of on the axis here. And kind of like the equator coming through the middle, you have these guys located here on that sort of plane in the middle of it. And again, that's sort of what is referred to as the equatorial position. Again, kind of like the equator going through the center, if you will, while the other one's sort of located on the axis there. So 5 electron pairs, 3 bonds, going to give you T-shape for the molecular geometry, triangular bipyramidal there for our electron pair geometry. The next sort of geometry that we have, if we look at our central atom here, we're also having 5 electron pairs around our central atom. So again, if we look at it like this, we have 1, 2, 3, 4, and 5 electron pairs. We also have, in this case, 4 bonds. So now we get this 4th bond in there. And again, the 5 electron pairs in terms of our electron pair geometry is going to be triangular bipyramidal. But again, with that 4th bond, these bonding guys are going to try to spread out. It's going to allow these other bonding guys to also spread out. And it actually gives a molecular geometry known as seesaw. Kind of like a seesaw, right? It kind of looks like one. Some people will also, in some books, will use another name. Some people will call this the distorted tetrahedral. You'll sometimes see distorted tetrahedral used for this geometry instead of seesaw. I think your book goes with seesaw, but some places will kind of use the other one as well. So if you see that, it basically represents this guy. But again, it kind of looks like a seesaw as you put on there. And again, our expanded octet sort of happening here. And again, with this extra bond here, they're able to kind of spread out as they can. And again, those non-bonding electrons going to spread out as well. Now we're going to look at what happens when we kind of get to 6 electron pairs around the central atom. So now with this guy here, you can see we have 6 electron pairs. No, 1, 2, 3, 4, 5, and 6. And in this case, we have 4 bonds. And again, once we move to 6 electron pairs, the electron pair geometry becomes octahedral. And what ends up happening is these 4 bonded guys sort of become on the same plane and basically kind of makes a square. Hence the name square planar would be our molecular geometry of square planar. So these 4 bonded guys all move within the same plane and make this sort of square arrangement. Obviously, our non-bonding electrons are going to spread out as far apart as possible. Remember, they don't really want to be near each other, so they kind of spread out to get some distance, why those other 4 bonded guys basically come together to make a square in this particular arrangement. Again, also an expanded octet here at 6 electron pairs are a total of 12 electrons around the central atom. So again, here we're talking about guys at sulfur left and right and down with perhaps the ability to do that. And our last geometry, thank goodness, right, is our central atom that has 6 electron pairs. So as you can see here, 1, 2, 3, 4, 5, and 6 electron pairs. And in this case, 5 bonds. So just like before, 6 electron pairs. Again, in terms of electron pair geometry, not going to change. It is going to be octahedral for electron pair. And in this case, we do end up getting 5 bonds. So again, these sort of 5 bonded guys try to spread out as best as possible. And a much better picture maybe over here. You kind of make a square on the bottom, and it's sort of a pyramid shape because you got that 5th bond kind of coming up to the top there. And we get what is known as square pyramidal for our molecular geometry. So as you can see, some of these geometries and stuff you probably have seen before. Some of them you might not have, especially these expanded octets or exceptions to the octet rule. Again, you do need to be able to identify the geometry, both the electron pair geometry and the molecular geometry for any type of Lewis structure that's either given to you or that you draw yourself. You don't have to worry about too much bond angles or anything like that. Maybe it'll be an extra credit question, bond angles, but you don't have to worry too much about it. Any questions on molecular geometry? Here's a table. It's not from your book, but I think you have a similar one. Again, here it kind of goes through the different geometries and that we talked about. And again, the electron geometry or electron pair geometry, the molecular geometry. Here's the bond angles, and here's some examples of those guys. And again, here, some of our expanded octets, again, getting into 5 and 6 electron pairs around the central atom. And there's our square planar and our square pyramid, as you can see. And you can see for a lot of these, again, a reminder, if you are sort of looking at bond angles or something like that, they are based on the electron pair geometry and how many electron pairs. And you typically, when you introduce those non-bonding electrons, as you can see kind of here, it becomes less than 90, for example, less than 120, less than sort of 90 degrees. So the bond angle is really, again, you don't have to worry too much about for our class, but just in general, they are based off of the electron pair geometry. And again, typically when you introduce those non-bonding electrons, as we talked about, because there's non-bonding electrons, there's not an actual bonded atom there. It gives the guys a little bit more flexibility. And that's why the bond angle typically becomes kind of less than it was before, because it's able to flex a little bit more than it did in the sort of place where it had all the bonds in there going on. So for example, what I'm talking about is here with this guy, which is 5 electron pairs, but this guy has 5 bonds. With all 5 of those bonded atoms there, it gets to about 120 and 90 degrees. If we get rid of one of the bonding atoms and kind of insert a non-bonding electron, it gives this whole molecule a little bit more room to sort of move around because it doesn't have that 5th bond locked into place. And with that empty spot there, again, the bond angle, as you can see, becomes a little less than 120 or 90 degrees in that particular case. So again, with the absence of that bonding pair, a little bit more flexibility in the overall shape of how that molecule can sort of bend. All right, so let's take a look at some here just to make sure. So let me draw some maybe structures we've seen before. Let's see. So this guy here, I think we've seen this guy. Actually, you know what? Let's do this one. Let's talk about this one here in just a second. Okay. So if we look at these guys here, again, just to look at some geometries here, why don't you take a second and make sure on the first three there, figure out the electron pair geometry and the molecular geometry and see what you come up with. All right, so if we look again at this guy here, we want to look at the central atom. This guy has 1, 2, 3, 4 electron pairs. It also has 3 bonds. So again, as we saw, the electron pair geometry should be tetrahedral because it has 4 electron pairs. But because it only has 3 bonds, the molecular geometry should be trigonal pyramid. Again, remember trigonal pyramid and trigonal planar are different. All right, looking at the central atom here, it has 1 electron pair and 2 electron pairs. Remember that double bonds count as only 1, so 2 electron pairs. Also has 2 bonds, which are the same ones that are circled. So something with 2 electron pairs is linear in terms of its electron pair geometry. And it's also linear in terms of its molecular geometry as well. Again, they have the same name because there's no dots on the central atom, so it would be the same. So linear for electron pair geometry, and again, linear for our molecular geometry in that particular one as well. And this guy here, if we look at it, 1, 2, 3, 4 electron pairs. Has only 2 bonds though. So 4 electron pairs in terms of electron pair geometry is going to be tetrahedral. And with those 2 bonds and those 2 non-bonding electrons, remember they're going to try to get away from each other. And again, the molecular geometry here going to be bent or V-shaped. Any question on those first few? So let's then talk about this little mess I was drawing over here. Try to clear some of that mess maybe. All right, just get rid of some of that there. Somewhere to work. All right. So in this particular sort of molecule, there's actually more than one central atom. And whenever you have a molecule that you have more than one central atom, you can do geometry, but you do the geometry for each central atom sort of separately. So when we look at this molecule, this carbon here is a central atom, this carbon here is a central atom, and this oxygen here is also a central atom. So in this particular example, we actually have 3 central atoms. And like I said, basically what you do is you take each one kind of individually. So for example, you could label this as carbon 1. And when we look at carbon number 1, essentially what you do is you count the electron pairs around it. So this would be 1, this would be 2, this would be 3. And this bond here you'd still count, which would be 4. I can't really do it on the screen, but essentially you kind of put your hand over this part of the molecule and just look at each one individually. So for carbon number 1, there's 4 electron pairs. And when we look at it, it's also 1, 2, 3, and 4 bonds. So if we just do the molecular geometry for it, the molecular geometry for that carbon number 1 is tetrahedral. Would be the molecular geometry. So then what you do is you essentially will go to the next central atom, kind of put your hand over everybody else that's there. And again, I can't really virtually do that here, but again, if we go to say this guy, we'll call him carbon number 2. For carbon number 2, we would count this bond over here, which would be 1 electron pair. Remember that our double bond here will also count as only 1 electron pair, so that's 2, and 1 electron pair this way. So carbon number 2 has 3 electron pairs. In terms of bonds, we have 1 bond here, 1 bond here, and again, our double bond counts again as only 1 bond as well, so it essentially has 3 bonds. So in terms of the molecular geometry for our guy in the middle, or carbon number 2, it basically has 3 electron pairs and 3 bonds. It is trigonal planar. So you can see these first 2 guys here actually have some different geometries because of the types of bonds that you got going on. So let's look at the very last guy, which is our oxygen. And our oxygen, we would do the same thing. Again, this bond would count for the oxygen as well. So that's 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So for the oxygen, it's got 4 electron pairs. It has, in this case, 1 bond here. I'll make it really thick. And it has 1 bond here for 2 bonds. So in this particular case, the oxygen at the end there actually has a molecular geometry of bent or V-shaped. So if you do draw something or come across something that has more than 1 central atom, what you essentially do is take each of them kind of individually, just kind of put your hand over the other part of the molecule and then count all the electron pairs and bonds that are there. Any question on that? So let's take a look and see here. Give you one to kind of do like that. So let's say we had all right, for each of the central atoms here, figure out the molecular geometry. So what's the molecular geometry of each center atom? And by the way, in case you're not sure, that's the center atom, that's the central atom, that's one, and this one. So take a moment or two and sort of figure out what you think the molecular geometry, not the electron pair geometry, just the molecular geometry is for each of those. Okay, so let's take a look. So starting with, say, this carbon here on our left, we want to, again, just pretty much isolate it. So electron pair here. Our triple bond, again, counts as basically one electron pair as well. So it has two electron pairs, also has two bonds. So the geometry, the molecular geometry of this guy is going to be linear in that case. Then we could go to the carbon next to it. Again, pretty much just isolate that carbon. I kind of scribbled it here, but again, this triple bond that was originally here, still only going to count as one electron pair. This is going to have another electron pair over here. So again, this guy as well also has two electron pairs and also two bonds, which means it is also going to be linear in terms of its molecular geometry. Now, when we go to this carbon here, it has one electron pair here, kind of circle it here, two electron pairs, three electron pairs, and four electron pairs. And each of those that I kind of circled were bonds as well. So it has four bonds. And again, four electron pairs and four bonds is going to give this guy tetrahedral in terms of its geometry. And lastly, if we kind of go to this oxygen here, again, one electron pair here, I'll turn it into a big circle, two electron pairs there. And obviously this is going to be three electron pairs and four electron pairs. Has only two bonds, the kind of big circles here on the outside. So something again with four electron pairs and two bonds in terms of molecular geometry will be bent or V-shaped. So again, you could apply geometry just like you normally would. If you have more than one central atom, basically, usually you just kind of put your hand over that part of the molecule and look and see how many electron pairs and bonds you have, and then move to the next one, put your hand over the other part of the molecule, and so forth. The key is, though, obviously, when you put your hand over it, the bond that's coming into there still counts, or the electron pairs still count for it. Question on geometry or how to deal with multiple central atoms. Okay, so the next thing we're going to talk about, we've sort of been talking about what's sometimes referred to as valence bond theory. And we're going to talk about sort of another sort of theory of bonding. And this theory of bonding sort of helps us see the bond angles that we see in these molecules. And this is what is known as hybridization. So hybridization is sort of a bonding model that helps us, like I said, sort of explain the geometries that we see, more so the bond angles that we see in certain molecules that we know. And valence bond model describes, again, a covalent bond, as we've been talking about, as this area where those orbitals basically overlap. So again, if we take our 1s orbital here in a hydrogen and our 1s, which again is a circle, as they overlap, this is the area where we believe, obviously, the theory is that's the area where they're sort of sharing electrons in that sort of overlapping area. And that's, again, what's going to sort of hold that bond together is that overlapping. Now, when we talk about sort of bonding that occurs between different orbitals, you have to remember that when we talked about sort of the shapes of those orbitals, for example, S's, as we just saw, are kind of a circle type shape. P's are more of a figure 8 type of deal. And in a sort of regular bonding, if you just kind of try to slap a S orbital together with a P orbital, obviously you can see there's sort of different shapes. They're obviously as well at different energy levels. So if you remember electron configuration, we had our S's, right? And then our P's are higher in energy. Our D's were sort of higher and so forth. So we have a lot of this sort of spread in terms of energy of these orbitals and also sort of the shapes of those orbitals when they try to come together. So the theory of sort of hybrid orbitals came about, and basically what hybrid orbitals are is we sort of combine both at like an s orbital, for example, and a p orbital, and we put them together. So we take an s orbital, p orbital, and put them together and make a new type of orbital, which is known as a hybrid orbital. And some of the advantages of hybrid orbitals in terms of bonding is what ends up happening, as we'll see in some of these pictures, is when we make these hybrid orbitals, we end up with orbitals that are the same shape. So now instead of putting together like a circle and a figure eight, you're going to put together two things that are essentially the same shape, which is going to allow them probably to come together a lot easier, a lot better. And in addition, instead of say mixing a s orbital that's here and a p orbital that's here together, you're now going to have hybrid orbitals that are the same shape, and they actually end up being the same in terms of energy. So everybody's the same in terms of energy. Everybody's kind of the same in terms of shape. And it makes for sort of better bonding, better overlapping of those orbitals that's going to happen. So when we take atomic orbitals and we talk about atomic orbitals, that's these guys here, like our S's or P's or D's, all those guys. And when we take them in the proper sort of energy and orientation, they are basically can be hybridized, which is basically just the mixing of those orbitals. And what ends up happening, like I said, is we end up with these hybrid orbitals, which again are basically the same shape. They're the same energy level. And again, that results in much better sort of overlap that happens. Now, the total number of hybrid orbitals that we're able to make is equal to the number of atomic orbitals that we combine. So for example, if I took what I got up there, if I took one s orbital and combined it with a p orbital, that is a combination of 1 and 2 atomic orbitals, which means what I will get is, I'll just draw it this way, 2 what are referred to as sp orbitals. So these are hybrid orbitals. sp, as you could imagine, the name means that you took an s orbital and you took a p orbital and you basically put them together. And we got a grand total of 2 hybrid orbitals here because we combined an s and a p, so 2 gives us 2 hybrid orbitals, and they're both sp orbitals. Both of those guys, we'll see the shape of it kind of in a second, but they both would have the exact same shape. Best I drew it there. They both would technically be the same energy as well. And again, that's going to allow sort of for better overlap to sort of happen and better bonding. And also sort of moves into why we see some of the bond angles that we do see. So let's talk about the sp orbital, which again is the simplest orbital that you could have. And sort of this picture over here, that's our s orbital, which is kind of the red circle. Our p orbital is kind of the bluish type guy there, our figure 8. When they kind of mix together, they end up forming 2 sp orbitals, and that's sort of these kidney shaped looking guys over here. Very badly drawn. I'll try. Sort of like this is sort of what it looks like. Very badly drawn there, but our kidneys type of little shaped here. Here's 1 sp orbital here, and over here would be 2 sp orbitals. Now that you get 2 sp orbitals, they end up being 180 degrees apart. We get 2 sp orbitals. That 2 number is important because it is related to the electron pair geometry, right? And if you remember, with our electron pair geometry, something with 2 electron pairs has a geometry of linear. So typically guys with a linear geometry will end up with a hybridization that's sp. So when we do this, sometimes this is sort of the easiest way to sort of think about it. We start with S's, just like we did with electron configuration, and there's just one. And then our P's, right, which there are 3 different orbitals, and then our D's, which are 5 different orbitals, right? So in this particular case, and when you do hybridization, you always kind of start here. And pretty much you count how many electron pairs, which is 2, which means 1, and then you got to come up here 2, and that gives us an s and a p orbital. It's going to be hybridized. Again, going to give us 2 sp hybrid orbitals that will happen. We also see that we have 2 unhybridized p orbitals that occur in that particular case as well. So for example, if we look at beryllium fluoride, these are the electrons that we find in beryllium. So again, if you go to beryllium on the periodic table there, beryllium is 4, which means its electron configuration is 1s2, 2s2. These 2 electrons here, these 2, are what we're talking about right here. So in the process of hybridization, what ends up happening is one of these electrons basically gets promoted up to the p orbitals. And you get that promotion of that electron. And it's at that point that our s orbital and one of these p orbitals will come together and hybridize to make our sp hybrid orbitals. Again, 2 of them, sp, each has 1 electron in it. And we could also see that we had 1 and 2 unhybridized p orbitals. So these 2 guys were not hybridized. They have no electrons in them at this point. Each of these have an electron. So visually, if you kind of want to kind of think about what's happening, this guy here, for example, would be able to bond with the fluorine, which would be one of our bonds. This guy here would be able to share an electron and bond with the fluorine. And that's where our bonds would come from the sp hybrid orbital of our beryllium and bonding to our fluorine on each of those guys. Again, they each have 1 electron, which means they could share 1 electron in this case. So if we drew BeF2 like we did before, if we went to the central atom like we did before, we would count 1 electron pair, 2 electron pairs, and essentially that little thing I drew there, you would go 1 electron pair, 2 electron pairs. So hybridization would be an S and a P basically. And that's how you could quickly sort of identify that guy would have sp hybridization in that particular case. The next type of hybridization that occurs is what is known as Sp2 hybridization. And much like the name sort of implies, you are going to take 1 s orbital and you're going to take 2 p orbitals and hybridize them. So down here in this little picture, again, that red is the s orbital. Here is a p orbital there. Here's another p orbital heading that way. And that is, again, an s and 2 p's. So again, if you count sort of that thing like I just did, we're taking an s and 2 p's, which means we're making an sp2, which is what that means. And since we're combining 1, 2, and 3 of these atomic orbitals, that will give us 1, 2, and 3 sp2 hybrid orbitals. And as you can see, one of those p orbitals will be unhybridized. So again, you can kind of see it has sort of that same sort of shape. There's 1 hybrid orbital, 2 hybrid orbitals, and 3 hybrid orbitals there. And if we think about it, that is 3 is the magic number there. And if we think about 3 electron pairs in terms of the electron pair geometry, that is something that is trigonal planar. So the electron pair geometry that sort of goes with this hybridization is something that is trigonal planar. 3 electron pairs will hybridize just like this. So an example of that is BF3 that we saw earlier. So again, what we're looking at here is the electrons from boron, which boron again is 5, which means 1s2, 2s2, 2p1. Its valence electrons, which are the ones involved in bonding, right, are these guys. 2 and 1 gives you 3 valence electrons, which is what we see here. Now, what's going to happen is as this goes through the hybridization process, same thing's going to happen. This electron in the lower energy level is going to go up. But just like what we did with electron configuration, it will actually end up, obviously, in the next box. So just like we did orbital diagrams for electron configuration, it should end up here in the next box. And what that means is we will get an electron in an s orbital, an electron in one p orbital, and two more p orbitals. And that's going to give us 1, 2, 3 hybrid orbitals. Again, each of these are now the same shape. They each have an electron, which allows them to make a bond. And again, we have this one orbital here that did not get hybridized, has no electron in it at this moment. And it's what's known as an unhybridized p orbital. Again, each of these hybrid orbitals can now make a bond with a fluorine, right? This guy could bond to the fluorine, this guy could bond to the fluorine, and this guy could bond to the fluorine. And again, that would be a bond between a sp2 hybrid orbital and the fluorine. And again, the easy way to figure that out is if you have the Lewis structure, which again, this is an incomplete octet as we talked about earlier. And again, you could just literally draw this thing like I've been doing and go, okay, it has 1 electron pair, 2 electron pairs, 3 electron pairs, 1 electron pair, 2 electron pairs, 3 electron pairs. I just combined an S and 2 P's, which means the hybridization here should be sp2 for our central atom. So that's really sort of the easiest way to sort of figure out hybridization is you want to count electron pairs. Just like before, as we will see shortly, if you have a double bond or a triple bond, just like you do with geometry, you count it as only 1 electron pair. So again, you sort of follow the same sort of geometry counting of electron pairs, double bond, triple bond, 1 electron pair. And literally, you can always start at the bottom here with S and just figure out how many sort of guys you use, kind of go in order, go up to the right, go up to the right if you need to get there. So sp2 hybridization, if it does that, you should have 3 sp2 orbitals, hybrid orbitals. And again, it goes with the geometry, electron pair geometry of trigonal planar. The next type of hybridization that we'll see is sp3 hybrid orbital. And sp3 hybrid orbital, much like the name implies, means that we're going to combine an s and all 3 of those p orbitals. So we're going to take an s and all 3. And since we're combining 4 atomic orbitals, which is 1 s orbital and 3 p orbitals, gives you 4, we are going to get 1, 2, 3, and 4 sp3 hybrid orbitals. Again, all the same shape, all the same energy level. And if you look here, you can kind of see our 4 guys coming together, our circle there, which is our S, our kind of 3 p orbitals. Might be hard to see the third one hidden back there. But when they come together, we do get these 1, 2, 3, and 4 hybrid orbitals. And again, that basically means 4 electron pairs. And if you remember, 4 electron pairs in terms of its geometry for electron pair geometry, the electron pair geometry is tetrahedral. So something that has tetrahedral geometry for its electron pair geometry will hybridize in the sp3 hybridization. And it gives us the bond angle, as you can see here, that we associate with tetrahedral, which is our 109.5 bond angle, just like our previous one with our here with our trigonal planar gives us that 120-degree bond angle, and the one before that, which was our SP, gave us the 180-degree bond angle, which is associated with our linear. So again, these hybridization or hybrid orbitals give us the bond angles that we see in these guys and that are associated with those sort of geometries, again, based on not the molecular geometry, but the electron pair geometry. So an example of that would be CH4. So again, what we're looking at here in terms of electrons is the carbon's electrons. Again, carbon number 6 there, and that would be 1s2, 2s2, 2p2. This being, again, carbon's valence electrons, the 4 electrons that we see here. So again, through this hybridization process where the s and the 3p orbitals are going to all come together, we're going to get that electron from the lower energy level. And again, as we've been talking about, it will fill the next orbital when it gets promoted up there. And all 4 of these guys, 1, 2, 3, and 4, will come together. And since we're combining 4 atomic orbitals here, we will get 4 hybrid orbitals. And each of those hybrid orbitals, in this particular case, does have an electron in it. And that's good because each of them can make a bond with hydrogen. And it would be a bond between the sp3 hybrid orbital in carbon and the 1s orbital in the hydrogen. Hydrogen will not hybridize because it only has 1 electron, so it won't go through hybridization, so it will just be 1. Again, the easier way to do that, if you just need to figure out the hybridization, is if you have your Lewis structure, just like we did before, 1, 2, 3, 4 electron pairs. And again, if you weren't sure, you could use this little schematic here and go 4. So 1, 2, 3, and 4. I just combined an S and 3 P's. That tells me that this hybridization is sp3 in that particular case. So again, that's sort of the simplest way. And in most cases, I would say, probably in most problems, 99.9% of the problems, you probably will just be asked, what is the hybridization? So you don't have to really draw any of these arrows or anything like that. You basically can just count the electron pairs, and it will correspond to a electron pair geometry that you know. And again, you could just always kind of go in this sort of scale like we have here on the right, and always start here and work your way up. And you could literally just kind of count off the hybridization when you look at it. Any question on that so far? So let's talk a little bit about some different types of bonds that result from these orbitals and sort of how they overlap. And let's talk about what happens in something like ammonia and water, where we actually have some non-bonding electrons sort of involved. So when these orbitals basically come kind of head on to each other, and that's what is sometimes referred to sort of head on or head overlap, basically they're coming straight at each other. So those 2 orbitals, like the S's, the P's, the hybrid orbitals, whatever they may be, they're just heading straight at each other. And when they head straight at each other, kind of like what we saw earlier, like when these 2 guys head straight at each other, we get that area of overlap between those orbitals. And that creates what's basically known as a sigma bond. So a sigma bond basically happens as they come straight head on to each other. There's an area of that overlapping where we're sharing electrons. And that's essentially, again, what is known as a sigma bond. So pretty much every single bond that you make, every sort of line that you draw on your Lewis structure, that's some type of bond, basically one line, those are basically all sigma bonds. So they're all kind of single bonds, if you will. They all result from those orbitals coming straight at each other and overlapping in that sort of fashion. Now, when we do get something like NH3, or we get something like water, we do get some other sort of things that occur when hybridization happens. So here's a sigma sort of bond here. Again, these 2 orbitals are coming straight at each other, heading straight for each other. And again, hard to see in this picture, but you get this area of overlap as they sort of squish together. And again, that's where we have our sharing of electrons and results in our sigma bond that occurs. So let's take a look at NH3 and sort of see how the hybridization works for something like NH3. Now, again, what we're looking at here is nitrogen's electrons. So again, nitrogen is 7, which would be 1s2, 2s2, 2p3. And these 5 electrons here are the valence electrons that we have in nitrogen. So there's 2, 3, 4, 5. So this nitrogen is going to go through hybridization. And what's going to happen is this electron, just like before, is going to come up. But now what we see up here is because we're at nitrogen, we actually do have electrons that are occupying each of these orbitals. So just like we talked about when we did electron configuration, they go into these orbitals one at a time, heading in the upwards direction, which means our 4th electron would actually now end up back over here when it does that promotion. And we're going to hybridize all of those guys. And one of these guys are going to be a result of these are all going to be, if we draw, why don't we draw this first so we can kind of see what we're looking at here. So first off, if we look at NH3 and we draw the Lewis structure, if we were to count the electron pairs, we have 1, 2, 3, and 4 electron pairs, right? So again, doesn't matter that some are non-bonding, doesn't matter if they're bonding, but nitrogen still has 4 electron pairs, which again is our tetrahedral geometry. But in terms of hybridization, again, if you just count like we did before, we're taking 1, 2, 3, and 4 in this case. And we basically are combining an s orbital and 3 p orbitals. So again, right off the bat, what that tells us is the hybridization of this guy is sp3. And that's what each of these represents. These are all sp3 hybrid orbitals. They all have the same shape. They all have the same energy. And because of the hybridization process, let's talk about where all these sort of electrons and stuff basically represent on our NH3 molecule. So we sort of draw our NH3 next to it. And what I'll do is maybe grab a different color here. So let's just say, for example, each of these 3 hybrid orbitals have the ability to make a bond. So we'll just do this guy to here, and we'll call that bond number 1, which would represent this bond right here. We'll say another one could bond to a hydrogen, which would be bond number 2, which would represent, say, this bond right here. This 3rd one has the ability to make a bond, right? The orbital can only have 2 electrons, so that has just 1, so it can bond with another one. And that will be number 3, which would be here. And now when we look at this right here, this hybrid orbital right out of the gate had 2 electrons in it. And just like an electron configuration, that means that that orbital is full. So it was full right out of the gate from those electrons coming in. And what those 2 electrons represent, we'll go this way, we'll call it 4. It represents the non-bonding electrons that we see here in nitrogen. That'll be number 4. And so hybridization can include, as you see here, are sort of part of the hybridization process. It also explains not only the bonds that we see, it also explains the non-bonding electrons that we see around the central atom, as indicated by that first box. Now, each of these bonds here, this nitrogen to hydrogen bond, this nitrogen to hydrogen bond, and this nitrogen to hydrogen bond. That all results from an overlap of an sp3 hybrid orbital and a 1s orbital in the hydrogen. So this comes from the hydrogen. This comes from the nitrogen in this case. And you basically have a head-to-head overlaps that's going to happen there. Those are all single bonds. It's really an easier way to look at it. The nitrogen to hydrogen bond is single, the other nitrogen to hydrogen bond is single, and the 3rd nitrogen to hydrogen bond is single. And that means that each of those are considered sigma bonds. And this guy would have 3 sigma bonds, sometimes abbreviated with a little sigma symbol there. And each of them would have that sort of hybridization. Any question on that there? So let's just go back and let's look at water, which was the other sort of example that we had. And if we look at water, if you draw water, which hopefully you know how to draw at this point, let's sort of walk through how you can figure out hybridization, maybe how you can figure out what's going on here. If this is all you have, and you want to know what the hybridization of the central atom is, the simple approach is just like we did before. You want to count the total number of electron pairs around oxygen. So oxygen has 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So again, if you weren't sure in terms of hybridization, that's where you could use this little kind of chart to figure it out. And again, 4, you pretty much just mark it. So 1, 2, 3, and 4. So I know here that basically I'm taking an s and 3 p orbitals, which means I do know already that the hybridization of this oxygen is going to be sp3. Any question on that? Again, it's as simple, don't overcomplicate it. It's as simple as counting the electron pairs and basically going right up that chart. Any questions on that? So because I know it's sp3 hybridization, I know that I am going to end up with 4 hybrid orbitals. That's because I combine 1 s orbital and, get the right fingers there, 3 p orbitals, which gives me a grand total of 4 atomic orbitals. And those 4 atomic orbitals are going to get me really 4 equal, in terms of energy, hybrid orbitals, which are all sp3. So how do I know in terms of electrons, you know, do they have 1 electron in those? Do they have 2 electrons in those? Again, what you would want to look at is oxygen, which is our central atom. And if we look at the electron configuration, 1s2, 2s2, 2p4, which means its valence electrons look something like this. Also means that if we were to draw its orbital diagram, right, we would have our 2p, which would have 2 electrons in it. We would also have our 3p orbitals, right? And it would have 4 electrons, which means up, 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 and down, just like we would do with electron configuration. So what's going to happen here is the same thing that we've been talking about. We're going to have an electron from the lower energy level work its way up. But when this one works its way up, it now needs to go here because our first box is already filled. And when it does so, all of those guys are going to sort of hybridize, but we're going to get up, down. The second guy now will have both of them filled. And this guy will have just 1. And our guy down here will have just 1. So when all 4 of these guys come together, what we see is we already have an orbital that's going to be hybridized that is filled. We also have another orbital that's hybridized that's going to be filled, which represents this one and this one. When these two hybridize, we're going to have just 1 electron in each. And again, this represents the oxygen here in water. And we can now sort of visualize perhaps where all our bonds are coming from. If we call this oxygen-hydrogen bond number 1, for example, it can make a bond right here with our hydrogen. If we call this oxygen-hydrogen bond number 2, this guy here in this orbital can make a bond. Now, what we have left when we look at water is a non-bonding electron pair there, and also a non-bonding electron pair there. And that would be represented by this hybrid orbital that was already full right off the bat, and this hybrid orbital that was full right off the bat. So in addition to sort of the bonds that are represented in these molecules, hybridization also, as you can see, accounts for the non-bonding electrons that we see as well. by the way, this water would have 2 sigma bonds. And that is basically these bonds right here between the sp3 in oxygen to the 1s orbital in hydrogen bond. And there would be 2 sigma bonds. Each of those would be the sigma bonds. Question on that? Now, we could also apply hybridization to ones where there are double bonds involved or even triple bonds involved. So in terms of just generally identifying hybridization, if you have a double bond or a triple bond, again, we count it just like we would do molecular geometry, our VSEPR geometry that we've been talking about. Again, if you have a double bond or a triple bond, it accounts as only 1 electron pair when you're doing geometry. But the existence of a double bond or a triple bond is a result of some different ways that these orbitals overlap. So before we just talked about a sigma bond, which is essentially a single bond. And again, that's a result of these orbitals heading head on to each other, straight at each other. Now, when we need to make a double bond or we need to make a triple bond, there's actually another way that these orbitals overlap. And the way these orbitals overlap are what is referred to as sideways overlap right here. So when we get orbitals that sideways overlap, and that usually is from p orbitals. And these are usually from unhybridized p orbitals. So when you think of a p orbital, again, it looks like this. And if we have 2 p orbitals, instead of them coming straight at each other, what ends up happening is they overlap sideways. So kind of above and below the plane of the molecule. These p orbitals, which are unhybridized, so they look just like regular p orbitals in that figure 8 sort of a way, they end up hybridizing sideways instead of heading straight at each other. The top sort of lobe of it overlaps with the bottom, and we get this sideways overlap. And that results in a type of bond which is known as a pi bond. So pi bonding is the bonds that you get to form really a double bond and a triple bond. As you can see here, these are our p orbitals. Again, instead of heading straight at each other, this is sort of the plane of the bond, kind of in the middle. They overlap kind of the sideways, and what you end up getting is this sort of sandwich of these orbitals above and below sort of the plane where they bond together. Forget that part of it. Don't worry about that one. And what that essentially means is, if you just want to kind of cut to the chase in terms of, you know, is it a sigma bond, is it a pi bond? This is sort of the easiest way to remember it. If you have a single bond, and when you draw a single bond, it's basically one line. And that first line that you draw to make a single bond, which is the only bond that you draw, is going to be a sigma bond. When you make a double bond, right? A double bond consists of one line and then 2 lines, right? So the first line that you draw is still a sigma bond. The second line that you draw is a pi bond. So both of these together make a double bond. So when you have a double bond, kind of the way you can kind of visualize it is, again, the first line that you draw is a sigma bond. To make the double bond, the second line that you draw is the pi bond. And then obviously when you get to a triple bond, you have 3 bonds that are there, or 3 lines that are written there. So when you get to a triple bond, you got 1, 2, and 3 lines. It's kind of big spaced out there, but the first line, just like before, is considered a sigma bond. Second line is a pi bond. And the third line is also a pi bond. So all three of those things together make what we call a triple bond. So a single bond is a sigma bond. So if you draw a Lewis structure, you go around and count all the single bonds. Those are going to be sigma bonds. If you have a double bond, one of the lines would be a sigma bond. The second line would be a pi bond. And if you have a triple bond, the first line would be a sigma bond. The second line would be a pi bond. And the third line would be a pi bond. So that's sort of the easiest way to look at something and try to identify, you know, how many sigma bonds are a hybridization that's going on there. Now we also can get into the expanded octet. So for example, let's take a look at like SF6, for example. I think I missed that S, but we'll go this way. All right. So again here, if we look at SF6, we got 1, 2, 3, 4, 5, 6 electron pairs. So again, if you weren't sure, you could do this little arrangement here. 1, 2, 3, 4, 5, and 6. That means I combined an S, I combined 3 p orbitals, sp3, and I also combined 2 d orbitals. So the hybridization of this expanded octet would be sp3d2. So obviously that hybridization sp3d2 goes with our electron pair geometry of octahedral, which means the one that we kind of skipped over was if we had, say, something like this. In this guy, electron pairs 1, 2, 3, 4, 5 electron pairs. And again, if we did 5 electron pairs, one, 2, 3, 4, and 5. In that case, I did an S, I did 3 Ps, and I did just 1 D. And that would be the hybridization here. And that obviously goes with our triangular bipyramidal. So hybridization really does go with sort of the electron pair geometry that we've been talking about. And really the easiest way to figure it out is just simply to count the electron pairs around wherever you're trying to apply the hybridization to. And again, you could literally check it off the list like we did here and figure out what the hybridization is. Any questions on that there? So let's take a look at a couple of things here. Let's say we had that one we saw earlier, maybe. Let's see. Let's just do a bunch of them here. Let's do this. And take a look at those guys we had earlier. I think this was them. Okay. So I want you to take a second or two and answer these questions. For all the ones that have arrows, what is the hybridization of all those? Again, for everybody that has arrows. And then also total number of sigma bonds in this guy. And total number of pi bonds. And same thing for the guy on the bottom. So for each of them, total number of sigma bonds in the entire molecule, total number of pi bonds in the entire molecule, and then also what is the hybridization of everybody that has an arrow. So I want you to take a couple of minutes and then we will talk about it. Again, you don't have to draw any arrows or boxes, just give me the hybridization and what the number of sigma bonds total is in each, and pi bonds. Okay, so since we're getting to the end, let's take a look. So remember, if you're doing hybridization, sometimes it's good to kind of make this little scale here to help you out. All right, so let's start with the guy top left here in terms of hybridization we'll start with. So again, we want to just look and sort of isolate this carbon by itself. It has 1, 2, 3, 4 electron pairs. So again, 1, 2, 3, and 4. That's basically an S and 3 Ps, which means the hybridization of this guy is sp3. Now, when we go to the carbon over here, it has 1 electron pair here. So 1 electron pair, 2 electron pairs. And again, remember our double bond here is going to count as just 1 electron pair. So that's actually 3 electron pairs on that. So again, starting at the bottom, 1, 2, and 3. that means that we took an S and two P's together, which means its hybridization would be sp2 in that case. Going to our oxygen, it has 1 electron pair here, 2 electron pairs here, 3 electron pairs here, and 4 electron pairs here. And that again would be 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs here. I took an S and 3 P's, which means the hybridization of this guy would be sp3. You could also sometimes apply hybridization to the outside atoms. Doesn't necessarily has to be the central in some cases. So if we do the same approach, double bond only going to count as 1 electron pair. This would then be 2 electron pairs, and this would be 3 electron pairs. So again, 1, 2, and 3 gives us S and 2 P's, which would be sp2. Any questions on the hybridization part of any of those guys? So while we're doing hybridization, let's continue down here. We'll get to the other part of the question in just a sec. So looking at our carbon here, this has 1 electron pair here. Again, even though there is a triple bond happening there, that still counts as only 1 electron pair. So that's a total of 2 electron pairs, which again gives us S and a P. And that's it. So this would be sp hybridized. Carbon next to it has the same triple bond, which counts as 1 electron pair. Has a single bond, which counts as 1 electron pair. That again is 2, which is the exact same thing we just had there, which is an S and a P, which means this is sp hybridization. Carbon here is 1 electron pair there, 2 electron pairs, 3 electron pairs, 4 electron pairs. So 1, 2, 3, and 4. That's going to be again an S and 3 P's, which means sp3 hybridization. And lastly, the oxygen, 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, going to come out the same. 1, 2, 3, and 4 is going to be sp3. Any questions on any of the hybridizations? Hydrogen does not hybridize, like I said before, so it has just a 1s orbital is the only electron it has. So for example, you could be very specific. You say this carbon here on the bottom would be a bond between the sp hybrid orbital in the carbon and the 1s atomic orbital in the hydrogen. So you could get very specific and figure out sort of what's involved in those bonds by doing the hybridization. First off, any questions on the hybridization part? All right, so let's finish up talking here on this question about how many sigma bonds, how many pi bonds we got going on. Let's start with sigma bonds. So remember, everywhere you pretty much have a single bond drawn in your Lewis structure will be a sigma bond. So looking at the guy on the top, we'll make them purple. There's 1 there, there's 2 there, there's 3 there, there's 4 there, there's 5 there, there's 6 there. Now remember, when you make a double bond, the first line in the double bond is also a sigma bond, so we'll do that. So in terms of sigma bonds, we have 1, 2, 3, 4, 5, 6, 7 total sigma bonds in this molecule. And in terms of pi bonds, remember that the pi bond is the second line that you draw for a double bond, or the third line that you draw for a triple bond. So this guy right here would be our 1 pi bond. Any questions on how to identify that for the top one? We could do the same approach for the bottom there. Go with the same color scheme. So let's do our sigma bonds. So we have 1 sigma bond here on the bottom, now purple. Remember, in a triple bond, the first line, if you will, is also a sigma bond. So that's 2. This is going to be 3 here. This is going to be 4 here. This is going to be 5 here. This is going to be 6 here. And this would be 7 here. So this has 7 sigma bonds. And lastly, in terms of pi bonds for the bottom guy there, remember that the second line that you draw to make the triple bond is a pi bond. And then the third line would be a pi bond, which means that it has 2 pi bonds down here. All right, any questions on obviously how to identify hybridization, how to identify how many sigma bonds or pi bonds there are? Again, this is probably representative of how the question would be asked, and what you need to do is, again, in most cases, you'll need to be able to draw the Lewis structure obviously correctly, and based on your Lewis structure, identify the hybridization that's going on for any of those atoms that could hybridize, and also figure out how many sigma bonds there are and pi bonds. Any questions on any of that that's going on? Okay, so that should wrap lecture. We went a little long today, so I tell you what, we'll start lab about 5 to 10. So 9:55, we'll start lab. If you haven't done so, make sure you do type here in the chat there. And other than that, I'll see everybody in lab today at 9:55.